Okay, in our last video, we left off at limitations of Arrhenius' theory. So let me just make sure that we're okay on this subject. When it says free proton, what that's talking about is in Arrhenius' theory, we have an acid such as hydrochloric acid. It's in an aqueous solution, so it breaks up into a hydrogen ion and a chloride ion. This hydrogen atom is what we call a free proton. Because remember, a hydrogen ion and a proton are interchangeable because they both have a mass of 1 and a charge of 1. Okay, so proton and hydrogen ions are interchangeable. So what happens if we show water, so instead of having this aqueous right here, we're going to actually show water in a solution. So when we do that, let's say we have HCl plus water. What happens is that this HCl, because you have a positive and negative charge, it's going to break up into ions when we put it in water. And when it does that, the hydrogen is going to be attracted to the water. So it's not going to be by itself on the product side like it is up here in Arrhenius' theory. And the reason why this happens is because this hydrogen has a high positive charge density right here. And it's going to seek out a negative charge other than with the chlorine because it's broken apart now into ions. And the only charge that has this negative would be the oxygen in the water. So here's what we're looking at. If we draw out a Lewis structure, here's our water. This hydrogen ion is going to come and bond to the water. So when it does that, because the oxygen is more negative, that hydrogen ion is going to bond to the oxygen. And then because we have an overall plus charge, and we're combining it with water, which is neutral, we're going to have an overall positive charge on the outside. This is what this is. This is called hydronium. I'm going to write that out. Hydronium ion. And in acids, a hydronium ion and a hydrogen ion both show us that an acid has been broken apart in either water or we can say in an aqueous solution because that means the same thing. So if we go back to our original equation, let me erase this. What we get here is that hydrogen breaking apart and bonding in the water, which is hydronium. And then the chlorine is now by itself, or I should say the chloride ion. And so that's what we get if we are showing the water in a reaction. The general formula for this looks like this. You get an HA. This is just representing any acid, so the hydrogen with any anion, plus water. That hydrogen is going to come. Ion, it's going to bond to the water to form hydronium, and then A, which represents the anion, is going to have a charge. So that's your basic form of a free proton in a free proton bonding with a water. Okay, the second and third limitations of Arrhenius' theory. Ammonia, which is NH3, does not contain hydroxide ions. Remember, ammonia is a weak base. We'll talk more about what that means in a little bit. It doesn't contain a hydroxide ion. And according to Arrhenius' theory, a base has to have a hydroxide. But ammonia is a base and it doesn't have one. So that's a second limitation. The third limitation is that Arrhenius only applies to reactions in an aqueous solution. So that means in a water solution. So that means that a solid state or a gas state would not be considered an acid or a base. We couldn't have those because it wasn't in an aqueous solution. Okay, so to solve this problem, two men came up with another theory. This is called the Bronsted-Lowry theory. And that name comes from those two men. And this was a broader view. And so what happened is that this viewpoint, this theory, overcame most of Arrhenius' theory's problems. that we just mentioned. So their theory is that an acid will donate a proton. So remember that a proton is interchangeable with a hydrogen. So whenever you're thinking about a hydrogen and proton interchangeable, a base will accept it. Okay, so now we have a lot more range on what types of formulas can be an acid or a base. So for example, we have hydrobromic acid plus water forms hydronium. There's a hydronium ion and a bromide. So we have to look at the entire equation to figure out what's an acid and what's a base. So right here, we're going to compare. This is already telling us it's our acid. Okay, so an acid, according to Bronsted-Lowry, donates. So if we notice, that hydrogen is going to come over and bond with the water, which is where we got the hydronium. And since the water takes the base, or accepts the base, since it accepts the hydrogen, it's going to act as a base. Right here, this acid is donating the hydrogen. So donating the hydrogen means it's an acid, accepting the hydrogen means it's a base, and here are our two products. Okay, let's look at this example down below, and notice that you can't really distinguish what's an acid and what's a base just on their formulas. So we have to look at the reactants and we have to look at the products. So let's look at this one. We have CH3NH2. The product that goes with this is CH3NH3. So what's the difference between the reactant and the product? Well, we've gained a hydrogen and a plus charge, so a hydronium ion. If we've gained this, it means we've accepted it. So if we accept a hydrogen, this means that this is a base. Then make sure that this makes sense. Let's look at the water and compare it to the hydroxide because those two are similar. Notice how we have lost a hydrogen and now we have a negative charge. So this one, we lost one, that means we donated it, which means that the water is acting as an acid in this situation. So you'll see those on your homework. And if it's not clearly defined, or even if you think it is, double check and make sure you look at the reactants and the products to figure out if it's an acid or a base. Okay, let's look at another example. Okay, let's say that we have C6, let's write this one up here, C6H5OH plus NH2 with a negative charge, and that produces C6H5O with a negative 1 charge plus NH3. And the question asks you to identify what's the acid and what's the base on the reactant side. It'll only ask you about what's happening with the reactants. So let's compare. This substance right there correlates with that product. Notice that the H is different, so we have lost, okay? This substance has donated an H, so that means that this is the acid right here. And then this NH2 with a negative charge, we're going to compare it to the ammonia on the product side. Notice that the difference is that we've gained a hydrogen or accepted a hydrogen. So remember, if we had accepted one, then this becomes the base. So in this scenario, our C6H5OH is the acid and the NH2 negative is the base. Okay. Okay, another term is called amphiprotic. This is a substance that can either donate or accept a proton. So two very common substances that do this is water, and this is called monohydrogen phosphate. Other substances that do this are monohydrogen sulfite and monohydrogen carbonate. Sometimes they just call them hydrogen carbonate and hydrogen sulfate. But it can either accept or donate a proton depending on the circumstances. So in this first example right here, notice if we compare the monohydrogen phosphate to phosphate on the product side, we've lost a hydrogen so we've donated a hydrogen, that's why it's the acid. The water in this example, if we compare it to the product side, we have hydronium. We've gained a hydrogen and a positive charge, so this one we've accepted it, and that's why that's the base. In the bottom example, again, we're going to compare. Here's our monohydrogen phosphate. We're going to compare it to dihydrogen phosphate. The difference here is that we have increased the product side by 1 hydrogen. That means we've accepted, which means that this is the base. And then if we compare the water to the hydroxide, we've lost a hydrogen. So that means we've donated it if we've lost it. And that means that this is an acid. So in the first example, our monohydrogen phosphate is an acid. In the second one, it's a base. In the first example, our water is a base, and in the second one, it's an acid. And it's all because of what's happening on the product side and what you're looking at. And that term again is called amphiprotic, when you can either act as an acid or a base. Okay, we will stop here.